Alright, so Assalamualaikum and good afternoon to all. First of all, I would like to apologize because I have seminar for today and tomorrow, 2 days seminar that is overlapping with our class schedule. So to replace our class, I make this recorded video for you. Alright, so if you have any questions, okay, regarding this chapter, please let me know. You can just ask me anytime. All right. So for today, we will look for the end topics for chapter 5, which is AC analysis for fats. Yeah. So before we have gone through the DC analysis, right? So for today, we will look into AC analysis, current analysis circuit. So first of all, let's do the fast revision from previous class. So as I mentioned, in FETs, which is a field effect transistor, we will focus for E Mosfet, right? We will focus for E Mosfet, right? So regarding for E Mosfet, the equation that is really important is this equation, yeah, this equation that you need to memorize. So this equation also known as Shockley's equation. Okay, Shockley's equation. So from this equation, okay, you can see that K is constant. Okay, K is a constant value, and also VT, which is the threshold voltage. So some books it represent as VGS TH. Some book it represent as VT. So both is same, which is the threshold voltage. So what is threshold voltage? Threshold voltage, if you look at this graph, it's where the value of voltage that turn on the device, turn on the MOSFET. Okay, so before the threshold voltage, there is no current flow because there is no because the device is not turning on. It is in an off condition. All right, it is in a off condition. All right. So yeah, okay, so from this Shockley's equation you can plot this transfer curve, okay, the graph. This is known as transfer curve graph, okay, where you can see the relation between VGS and drain current. All right, so from this equation, from this Shockley's equation, you can rearrange to find the value of K if ID on and VGS on value is given to you. All right, so ID on and VGS on, you can get this value. Sometimes it's written to you. Sometimes you can get this value from this graph. Yeah, for example, you choose any point, 1 point for VGS, and you will get the reading for drain current, and you replace inside this equation. And threshold voltage you can also get from this graph, yeah, and you can always calculate K by rearranging this formula. All right, so another thing that you need to know for MOSFET for DC analysis, when IG is approximately 0 ampere, which is no currents flow inside the IG, which is this drain, this at this gate, yeah, there is no current flow. So it means that IG is equals to 0. So since there is no current flow at this area, at this gate, at this gate, at this gate, yeah, it means that the value of currents that flow inside drain is equals with the value of currents that flow at source. So ID is equals to IS. All right, so these two relation is very useful in order for you to solve the voltage divider biasing circuit. Okay, so actually we have lots of bias circuit. For example, we have feedback drain. Okay, we have feedback drain. I think there is an example I explained to you in previous slides, right? In previous class slides. So that are just example. In your exam, okay, in your exam, it will comes out this circuit, okay, only this circuit. voltage divider biasing circuit. So let's focus for this circuit, all right? So the configuration of this circuit is same with BJT, okay, where there is a R1, R2, RD, and RS, okay? So in order for you to solve this circuit, first of all, what you need to do is you need to plot the transfer curves. So for you to plot this transfer curve, again, you need to use this Shockley's equation. Once you plot this curve, you need another you need another line, which is, you need another graph, which is DC load line. Okay, how to plot this graph? You need to use your input loop. Okay, input loop is the VGS loop. Okay, always VGS loop. Okay, always VGS loop. So for you to solve this, yeah, we also need to use the Thevenin theorem. So please refer to the previous class lesson. Okay, so from this input loop, you can get the y-intercept value and also x-intercept value. Okay, so once you get this DC load line, okay, once you plot this DC load line, you can find there is a cross section between DC load line and transfer curves. So that cross section will be the Q point. So again, what is Q point? Q point is the operating point for the device. So the operating point from the Q point, yeah, from the operating point, you can get the value of VGS at the Q point and also the value of current ID at the Q point. So by using this value of current at the Q point, you can find the value of output loop, yeah, VDS loop. Okay, you can find the value of VDS using the output loop. All right. So these are the first recap from previous class. For today, we will focus about AC analysis. So first of all, for AC analysis, it is famous with transconductance factor, which is GM. So GM can be solved using mathematical and also graphical, that we will learn later on. And also we will learn about AC equivalent circuit, how to draw AC equivalent circuit. We will discuss also about resistance RDS, and we will discuss about e-MOSFET bias circuit, okay, which is, we will focus more about voltage divider bias. Right. So first of all, what is transconductance factor? So for BJT, okay, as I mentioned earlier, BJT is a current control device. Why we call as current control device? Because currents that flow in the collector is based on currents that flow at base, right, with the gain factor of beta. For FET, why it is called as voltage control device? Because based from the Shockley's equation, ID is equals K VGS minus VGSTH squared. Okay, so that's why it is known as voltage control device. So for both cases, yeah, for BJT and FET, both cases, output current is controlled variable. The output current is controlled variable. So BJT had an amplification of beta. For BJT, the amplification is beta. But for FET, the transconductance, yeah, the amplification, the FET has a transconductance factor which is GM. All right. So the gate to source voltage controls the gate to source voltage controls the drain to source channel current of an FET. All right. So for DC, gate to source voltage control the level of DC drain current through the relationship of Shockley's equation, as I mentioned earlier. And the change in drain current, okay, change in drain current is result from change in gate to source voltage. Okay, so change in drain current is result by changing the gate to source voltage, right? Because these two value is constant, it can't be changed. Only this, if you change this value, it will change of drain current at drain value too. Okay, and it can be determined using the transconductance factor, which is GM. So another formula which is related to GM, which is the transconductance, is delta ID. Okay, changes of delta ID is equals to GM times with changes of VGS. Okay, changes of delta ID, okay, changes of drain current is a result from the change in gate to source voltage. So you can determine GM. Okay, so the gain factor is the transconductance factor GM. So GM, this equation, okay, this formula, we can rewrite and it's gonna be look like this. It will look like this, right? So another thing, you can relate this, try to relate this equation with the ohmic law, which is V equals to IR, where R value is constant, right? But V and I value can be changeable. So R is equals to delta V over delta I, or V over I. So if you look at these two equations, there is a relation where GM is equals to I over R, where R is constant. Okay, where R is constant. Alright, so what is the meaning of transconductance actually? So the trans is a prefix, yeah? In the terminology, it's applied to GM. Okay, so this trans is applied to GM that reveals that it is established a relationship between the output, okay, between the output and the input quantity. Okay, so between the output, which is I delta ID, and input quantity. So the root word conductance, okay, the root word conductance, it is because the GM is determined by a voltage to current ratio. Okay, so that's why it is used words of conductance, because GM can be determined using the voltage to current ratio, which is similar to the ratio that is used for the resistor. Okay, for the resistor. So that's why the words is transconductance. So this is just extra knowledge for you. Okay. All right. So let's look into how we want to define, or how we want to determine GM from the graph. Okay, so if you still remember, as I mentioned earlier, there are two methods, right, to define GM. One is graphical method and another method is through mathematical method. So let's look how to determine GM using the graphical method. So GM can be determined, okay, you will get the value is based on the based on this graph, yeah, VGS ID relation graph. It is also equals to the slope of tangent, which is the gradient of the graph, which is symboled as M, where M can be defined with the delta Y over delta X, right? If you still remember, this is mathematics, right? M, which is the gradient of a slope, can be calculated using the delta Y over delta X, right? So in this case, delta Y will be any changes value at ID, okay, current that flow inside the drain, and delta S is the any changes value between voltage at gate to source. So delta ID divide with delta VGS is equal with the slope at Q point. Okay, usually GM we will calculate at the Q point, because Q point is the optimum operating for the device, right? So note that GM here at this point and GM at this point is different with GM at this point. So it is best to choose the value of GM at Q point always, yeah. So it can be calculated, yeah, using this formula again, from this formula. So at this Q point, okay, try to draw the tangent line. Okay, so you can see that delta ID, okay, value of delta ID, which is the changes of value at this point. Okay, this is delta ID, and then this is the value of delta VGS, right? So you can get the value of GM. So these are the graphical how you want to determine GM. So I think that this is not too difficult for you to define GM using the graphical method. So let's look at another method, which is the mathematical methods, how to define the GM. So from this, for the mathematical methods, okay, you need to derive, okay, from the transfer equation to determine GM, okay, as an operating point. So GM, you need to derive from the transfer equation. What is transfer equation? Which is also the Shockley's equation, which is ID equals to K VGS minus VT squared. Alright, so this is also known as transfer equation or Shockley's equation. So from this equation, so GM is delta ID over delta VGS, right? DID, differentiate ID over differentiate VGS. So ID can be replaced with this equation inside here, and since that K is constant, you can bring K at the front, and you can derive this equation, and the final answer you will get GM is equals to 2K VGS minus VGS threshold. Right, so since that we know ID is equals to K VGS minus VT squared, you can rewrite this formula as ID over K square root equals to VGS minus VT, right? So you can put inside here, and it can be rewrite as below. GM is equals to 2K square root ID over K, and it can be rewrite again as 2 square root K ID. So if you want to define GM, okay, based on mathematical definition, if you are given information of VGS threshold, okay, the threshold value, of course you can use this equation. But if threshold value is not given to you, okay, so you can derive with this formula. Okay, so so both of this is same. So how you want to choose which formula that you want to use is based on what information is given to you, okay, or what information that you have. All right, next. All right, so for GM, okay, usually transconductance is provided on the specification sheet, but on the specification sheet, it is not written as GM. It is written as YFS. All right. So on the specification sheet, so what is specification sheet? Is if you still remember, when you buy any device, it will comes together with the specification sheet that will give you all information about the device, right? The specific information about the device that you bought. So inside that specification sheet for MOSFET, GM is written as YFS. So what is the meaning of YFS? Y actually indicates the meaning of admittance equivalent circuit. Okay, Y indicates the meaning of admittance equivalent circuit. F signifies the forward transfer, okay, forward transfer parameter, and S means that it is the source terminal. It is connected to the source terminal. So GM is always equals to YFS. All right. So these are for MOSFET equivalent circuit. Okay, how to draw a MOSFET equivalent circuit, MOSFET equivalent circuit. All right, so MOSFET, as I mentioned earlier, there are two types of channel. One is P channel, okay, P channel. One is SN channel, right? So N channel or P channel. How you want to differentiate between P channel and N channel is by looking at the pointing arrow here. If the arrow is pointing against the gate, okay, it pointing outward from the gate, it is a P channel. But if the arrow is pointing toward the gate, it is a N channel, right? So, but for both channel, the the drawing for AC equivalent circuit is same. Okay, so you can see this is the gate. Okay, this is for the gate parameter, and then so gate is connected to it is not connected to drain, but it is close to drain. So drain, okay, and then drain is connected actually to the source. Okay, it's connected to source here, and between drain and source there is a GM-VGS. So what is GM-VGS? GM-VGS is the meaning of GM-VGS. It means that the current, okay, the current that flow inside here between at drain and source is controlled by the value of gate source voltage. Okay, the current that flow inside here is controlled by gate source voltage. Okay, and you can see that the pointing arrow is showing downward. So what is that meaning? Okay, the meaning of a pointing arrow showing downward, it means that the drain to source, okay, there is a inversion phase. Okay, there is an inversion phase shift between output and input voltage. Okay, this is the input part. This is the output part. Okay, this is the output part, and there is an inversion phase which is 180 degrees. Okay, 180 degrees. So it means that if the phase for the output part is positive, the output will be negative because there is a phase inversion 180 degrees. All right. So at drain and source, there's also RD, resistor RD here connected at this parallelly connected here, and some book it is represented as RDS, which is drain source resistor. Some book it represents as RD, so both are same. Okay, so this RD resistance, this RD resistor sometimes can be ignored. Okay, sometimes can be ignored. Why? Because the value of the resistor at this resistor is too large. So it means that the current cannot flow inside this resistor because the value is too large. So it can leave as open circuit. Okay, it can be leave as an open circuit. All right. So these are how the MOSFET AC equivalent circuit looks like. Okay, so GM as based from the previous slide is equals to YFS. Okay, so RD as we look at the previous slides, GM is equals to 1 over R. So it means that RD is equals to 1 over YOS. Okay, what is YOS? I'm gonna explain later on. Okay, first of all, before I explain the YOS, what is that? For PMOS, okay, how about P channel? Okay, the P channel, the configuration AC equivalent circuit is same as this, same as N channel, but the only difference is the pointing source. Yeah, this pointing, it will look upward. Different with N channel, it will look downward. For P channel, it will look upward, and the polarity of VGS, this VGS polarity will change into VSG. So it means that this will be positive, this is going to be negative. Okay, so it will be VSG for P channel. Others is same. Okay, RD is same. Others is same. Only these two is different, which is the source pointing and the polarity of the VGS. Okay. All right. So let's look. What is resistance RD, or also known as RDS? Okay, the output impedance ZO typically appear as YOS inside the specification sheet. Okay, YOS. So this is usually mentioned as input impedance ZI, and this is actually mentioned as output impedance ZO. So this ZO usually is represented as YOS. Okay, YOS with the unit of micro S. So what is the meaning of YOS? Just now YFS, you know, yeah. Y is means of admittance equivalent. F is a forward parameter. S is the source terminal, right? So for YOS, Y is same. It is a admittance equivalent circuit. O signify the output network, okay, and S signify the terminal source. Okay, so that's why because it is located at output, so it is OS. Yeah, the terminal is still the source terminal. All right, YOS. So ZO can be written equals to RD, and since that we know GM is equals to 1 over R, so RD is and GM is also same as Y, right? So it is can be written as RD equals to 1 over YOS, all right? So this is for the output. Yeah? So MOSFET output resistance located between source and drain terminal. Okay, this one. It is located between source and drain terminal RD. This RD, yeah. And RD has a very high value normally. Okay, it has a very high value. In small signal analysis, the value can be neglected. Okay, in a small signal analysis, this value can be neglected. Okay, you can omit this value because it will leave the circuit as an open circuit. Alright, and it can be calculated. But if you want to calculate, this RDS can be calculated from the drain source characteristic graph. Okay, how? You can, if you want to calculate, you can calculate using this graph. Okay, so I think you already know this transfer curve graph, right? So together with this transfer graph, you can also plot this drain source characteristic graph, where the y-axis is the VGS, yeah. Sorry, VDS, not VGS, but VDS, yeah, drain source, yeah. And the x-axis is VDS, the y-axis is drain current, all right. And this value, okay, this is the VGS value. So you can see when VGS is equals to 8 volts, yeah, for example, this is VGS, right? This is VGS value. When VGS is equals to 8 volt, the value of VDS, it will increase. At some point, it will become a saturation. It will become saturated, and so there is no changes of value of drain current, and value of drain current become maximum. Okay, so when you change the gate source value to other point, for example, for here at 7 volts, yeah, the drain to source value current, yeah, will increase. At some point, the drain current will become maximum. So if you change the DS value, voltage at DS, if you keep increasing, there will not increase in drain current. It will become saturated, and you can see that the value of the current value is 7. So these are the examples. So drain source characteristic graph is where the x-axis is the drain source, the y-axis is the drain current, and if you're changing the gate source value, you can see that the value of drain source voltage and drain current is changing as well, and at some point it will become saturated. Okay, so from this graph, okay, from this drain source characteristic graph, you can get the value of RD. You can calculate the value of RD, where still remember, yeah, R is 1 over G. G, if you still remember at the beginning, I said G can be defined using graphical method, where G is delta ID. Okay, can be defined using the transfer curve, right? Where delta ID over delta VGS, right? So for you to define R, it will be the other way around, where R is, we're gonna be X, since that it is 1 over G, so it will be delta X over delta Y. Okay, delta x over delta y, where the origin is actually like this, 1 over delta y over delta x. So it can be rewrite as like this. So as this resistor can be defined from drain source characteristic graph. So at this point, so R, for example, yeah, at Q point, usually any value that you want to define from this graph, usually we will get choose the Q point value. Okay, so the Q point is here. So if you want to find the value of resistor RD, so it will, since that it is delta X over delta Y, so it will be delta VDS, okay, delta VDS divide with delta ID, where the value of GS is always minus 1 volt. It's always constant. Okay, so you will get the value of resistor, this resistor, okay, resistance RD. Okay, so these are the values, these are the formulas, and note that always when you want to find RDS, the value of VGS is always at Q point and always constant. Okay, for example, when the VGS is minus 2, let's say the Q point is here. Okay, the Q point is here, so it means that, it means that you need to draw the tangent line, okay, that touch this graph, okay, this point, and then it will be delta VDS here. This is delta ID. So RD, okay, at this point, which is delta VDS over delta ID, when the VGS is equals to minus 2, VGSQ equals to minus 2. So VGS value is always constant. Yeah? Remain constant when RD is determined. Alright. Okay, so let's look the MOSFET configurations. Yeah? So MOSFET configuration, same as BJT. Still remember, BJT have 3 types of configuration. We have common emitter, we have common base, and we have common collector, right? So same as MOSFET, we also has common for each gate that we have. Since the MOSFET we have gate, drain, and source, so we have common source, we have common drain, and we have common gate. So in this course, we will focus on common source, right? So these are the example of the circuits. Yeah. So these are common source amplifier circuit with bypass capacitor without RDS. So RDS is not considered inside this circuit, and there is a bypass capacitor. So remember, yeah, bypass capacitor is a capacitor that connected to this source. Yeah, bypass capacitor. So these are coupled capacitor. These are bypass capacitor. All right. So how to draw the AC equivalent circuit? It will look like this. It will look like this, where this coupled capacitor will be short, right? Still remember, right? This capacitor will be short. Okay, will be short circuit, and this VDD, which is the DC source, will be ground. Okay, so it will look like VS. So VS source is here, and then there is a resistor here, okay, which is actually RS. So RS resistor here. So VIRS, and then there is a gate. It is connected. It is connected to gate. This is gate. This is drain, and this is source. So it is connected to gate, and parallelly with this resistor, there are RG resistor. Okay, there are RG resistor, and then what you need to pay attention is where is the impedance, input impedance and output impedance. So you see the input impedance, it's already mentioned that is before RG and after RS. So RS is not included or is not involved when you want to calculate the input impedance. And output impedance, it is before load resistance. So for you to calculate the output impedance, you don't have to involve the load resistance value. Okay, So the input impedance is here, and then drain. Yeah, for drain there is a RD. Okay, drain RD, and then both is connected to the ground. Yeah, this is ground, and then this is also ground, and then the source. Get the source. So the source is here. So GM VGS. So GM VGS, it means that the currents that flow between drain and source is controlled by the voltage of VGS voltage. Okay, and then RL, okay, load resistance is located at here, okay, parallel with RD, and the output voltage is at the load resistance. And then RS, if you realize there is no RS at this AC equivalent circuit. Why? Because there is a bypass capacitor here. Since that there is a bypass capacitor parallelly connected with this resistance, so RS is not included because the low impedance. Yeah, RS is not included because low impedance DANCE, yeah, will make this short, this resistor short. Okay, because of the low impedance that will shorting the resistor, and in fact it can be neglected for this AC equivalent. Okay, it is shorted at this part. Okay, so there is no RS inside here. Okay, so once you have draw like this, what you need to do is, based on the information, look back at the question, what the question asks. If the question asks for you to calculate the input impedance, so the input impedance is here, so it seems that the input impedance is no relation with this resistance value, so ZI is always same with the value of RG. Okay, RG. And for the output impedance, since that the output impedance is here and RDS is not taken into account in this AC equivalent circuit, so output impedance is always the same value with the RD. But if the resistance RDS is considered, if there is a resistance RD, so it means that the output impedance will be RD parallel with this RD. Okay, so be careful. Look, either the RDS is considered or not inside the circuit. It will mention to you. All right. So for no load voltage gain, okay, for the voltage gain at no load, it means that the voltage gain before the load. Okay, the voltage gain at this point. Okay, at this point, not related to load, and at this point. So if you want to calculate, V output at no load is equals to, okay, there's no RD in this case, right? So V output at no load, so it means that you don't have to consider this load. So it is negative GM. Why negative? Because this is positive, this is negative. So this is negative. Based on the Kirchhoff's law, it comes out negative. Negative GM VGS times with RD. Okay, that is the output, and then the input is always VGS. Yeah, this is the input. This is the input. The input value. Yeah. So VI is equals to VGS. So for the voltage gain, it is always output divide with input, right? Output divide with input. So it will be minus GM VGS RD over VGS value, and VGS can be cancelled, so it will leave to you minus GM RD value. Okay, so if this value, each of this value is given, so you can just replace this and you can get the value of voltage gain. All right, so let's look at this example. Okay, so this example, what they ask is find AV voltage gain, okay, at AV, okay, voltage gain of AV, which is no load. All right, and then AVS, which is voltage gain at here. Okay, voltage gain at here and voltage gain at here. And it's mentioned that it is without RDS. So you don't have to consider the RDS. Okay, so it's give to you the AC equivalent circuit already. So first of all, for you to calculate the voltage gain, okay, voltage gain AV, it is equals to V output over V input. Okay, V output over V input. So first of all, you need to calculate what is the output voltage first. So output voltage is voltage that flow inside here. Okay, flow inside here. So RL, currents that flow inside here, RL over RL, O, okay, currents that flow inside here, VO is same with the voltage output, is same with IL RL, right? IL RL. So IL is the currents that flow inside here, which is RL, which is the source of voltage. AV VI divide, if you want to find the currents, right? So AV VI divide by the value of resistance RO plus RL, right? RO plus RL. So this is the value of current, and then times with the RL. So you will get the output value of voltage. And then VI is RL plus O, AV and L, and VI is always VI because it is not considered at this point, right? VI is from this point. Okay, all right, so VI will be VI. So since that VI is times with VI, so this VI can be cut off. Yeah, this VI can be cut off, so it will leave to you RL over RL plus RO, AV no load, AV no load here, right? AV no load, which is this value. And since that AV no load, as mentioned earlier, it is equals to minus GM RD. Okay, so you can replace inside here. So it will be like this. So the answer will be like this. This is the final answer. All right. Next, you need to find the value of gain at AVS. This VS, yeah. So it means that this output is relating to this source. Yeah? So you have to consider RS2 inside this equation here, because you are considering at this point, okay, the whole AC equivalent circuit. So VO over VS is also equals to VO over VI times VI over VS. Okay, so when you cancel this both, you will get this one, right? So VO VI you don't have to calculate again. So VO VI you don't have to calculate again because the value, you can use this value. What you need to know and what you need to calculate is only VI over VS. So VI over VS is the impedance. Okay, the impedance Z, sorry, this, I can't go backward anymore. So this is, sorry. So this is ZI, right? So this is impedance input. So the input impedance over the input impedance plus RS. So these are the flow of currents. Yeah, the flow of currents is same with the flow of current is same for this at this point, right? At this circuit. So VI is equals to, yeah, VI is equals to I times ZI, which is the input impedance at here. I times ZI. So the value of I is equals to, VS over RS plus R1, right? RS plus ZI. So because this is input impedance, sorry, the input impedance is here, so there's no longer RI, but it's going to be ZI. Okay, RS plus ZI. Okay, so this is input impedance. So since that you need to find VI over VS, so rearrange this equation. It will be VI over VS equals to ZI over RS plus ZI. Okay, ZI over RS plus ZI. Okay, so you can just replace inside this equation, this equation, so you will get your final answer like this. Okay, so if the value is given to you, you can just replace all this value. Okay, alright. So let's look for another example. Common source E MOSFET with voltage divider. So this is not a voltage divider circuit, right? This is not a voltage divider circuit yet. This is only the common source amplifier. So let's look when the common source with the voltage divider bias. Okay, so since this is also without source signal, so it means that there is no source signal here. Okay, so only with the V input, VDD, and V output, and there is also a bypass capacitor here. Okay, note that there is a bypass capacitor that connected to RS. So same as just now, RS will be short circuit, yeah, if you redraw again. So this circuit, if you draw the AC equivalent circuit, it will look like this. R1 and R2 is parallel. R1 and R2 is parallel. Yeah, R1 and R2 is parallel. And then RD, okay, RD. And since that there is no mention here that without, it is not mentioned without RDS, so you need to consider the RDS. Yeah, so you need to consider the RD or RDS, so it will be located at here. Okay, so this is the drain signal, this is the drain, this is the source, this is the gate, this is R1 and R2. The input impedance is at here point, which is at R1 and R2. So it means that the input impedance is at here. The output impedance is, the output impedance is at this, yeah, at VO. So the output impedance is here. So bypass RS, yeah. So RS is not included inside this AC equivalent circuit. So how to find the input impedance? So the input impedance, okay, the input impedance, since that it is located here, so the value of input impedance is the parallel value of R1 and R2, yeah. So it will be 1 over R1 plus 1 over R2, 1 over ZI. So rearrange this, you will get the answer for the input impedance. For the output impedance, since that the output impedance is located here, it is also parallel for both. So ZO, 1 over ZO is equals to 1 over RD plus 1 over R capital D. Yeah, this one. So the value is this. This is for the output impedance. For the voltage gain, for if it is without no load, okay, so the voltage gain, so there's no load here, so the voltage gain is at this point, yeah. So it will be minus GM VGS, yeah, because it is because of the minus, yeah, minus GM VGS, and then RD over RD here, okay. All right, so this is the example if how you want to calculate when there is a RD and the input impedance is located before the R1 and R2, and the output impedance is located after RD and RDS. But if the value of RD, okay, how you want to know if you want to consider the value of RD or not? If the value of RD, is 10 times larger, than value of this RD, so it means that you can neglect this RD because it is too big, so the currents will not flow here. It will leave as an open circuit. Okay, it will leave as an open circuit. All right, but if this value of RD is less, not not larger or bigger than 10 RD, so you need to consider by parallelly connected with this RD. Okay, so look at the value of RD. Right? So if the value of RD 10 times larger with this value of RD, so it will leave to you ZO is equals to RD, even though they didn't mention inside the equations that without RDS or RDS can be neglected. Yeah. So this is another example, which is the common source in Mosfet AC analysis unbypassed RS. So it means that at the RS there is no capacitor located here. So it is an unbypassed RS. So the input impedance is located at here, and the output impedance is located at here. Right. So how to solve this equation? So you cannot on this time you cannot neglect this RS resistor anymore. You need to parallelly connect it to this resistor. Okay, so how it will looks like? It will looks like this. Okay, it will looks like this, and in this case you can ignore. Okay, just ignore the RDS. Okay, we assume the RDS is bigger. Okay, but inside for real question, before ignoring the RDS, please check first the value of RDS. Yeah, is it too big or not too big? Alright, so in this case we are ignoring the RDS. So the input impedance Zi, since that it is located at this point, so it is parallel with RG, so Zi is equals to RG. Alright, and for the output impedance Zo, we will set that Vi is equals to 0, so it means that there is no voltage flow inside here. So Vg, this is Vg, this is Vs, right? Vg is at this point, Vs is at this point. So Vg, it will be 0 volts. Yeah, Vg will be 0 volts. So when Vg is 0, VGS, the value of VGS is equals to minus Vs. Okay, minus Vs. So minus Gm VGS at this point, yeah, at this output, minus Gm VGS is equals to, this is currents that flow at the output. This is current flow that IT. So current flow here is IO plus ID, right? So IO plus ID times with GM VG, IO plus ID is equals to minus GM VGS, right? And then another equation is VS. Yeah? At this VS, yeah, minus VS is equals to minus RS. Why it is minus? Because it is different polarity with the output, right? So minus RS times with the currents that flow inside here, IO plus ID. So it is another equation. So you can put, insert 2 in 1 or 1 in 2, either one, you will get this equation. So if you rearrange this equation, you will get this equation, and you can find that one of the currents is minus. So what is that minus means? So it means that the polarity is different. Okay, the polarity is different with this polarity. So you can just ignore the minus because it means that the polarity is different, but the value is still same. So you can see that ID, so you can just ignore this minus here, because the polarity is different with this. So that's why there is minus here, but the value is still same, so you can just ignore this minus. Yeah, so ID is equals to GMRS plus 1, IO is equals to GMRS plus 1. So this is same. So it means that ID is equals to IO. So for VO here, for VO, which is parallel to this RD, yeah? So VO same with VRD. So VO, you can use either ID value or IO value. Both are same. You will get the value of VO. So ZO, okay, ZO is equals to VO over IO, which is equals to RD. Alright? I hope here is clear. Okay, maybe after this you can try to solve this equation again. So once you try, you will understand how it can be derived like this. Right? So next, this is the common source Mosfet AC analysis for unbypassed RS, which is same as this. What we will do is, now we will need to calculate the voltage gain. So if you want to calculate the voltage gain, yeah, no load voltage gain, this is no load, yeah, in this case no load. So VO no load means that we will ignore VO no, VO no load means that there is no relation with with the value of RS here. Okay, with the value of RS here for at the output. Yeah, since that there is no current flow, we assume that there is no current flow here. So the VO output value is minus GM VGS that flow here, and then RD. Okay, so VO here. So the VO here. So this is the value of VO, and then over VI. So the value of VI here is VGS. Okay, VGS plus with this VGS GM VGS VGS RS. So it means that there is no since we assume that there is no external source will produce from here, so it means that the V input is totally from this part, okay, which is VGS plus GM VGS and this RS. Yeah, so you can rearrange the equation, you can factorize the VGS, and it will leave to you like this. Okay, so VO no load over VI, so it will give to you GM, so because this VGS can be cancelled, so minus GM RD over 1 plus GM RS. So minus here means there is a phase inversion, which is the input wave is different with the output wave. There is an inversion of output wave. Yeah. So these are the how you want to. These are the example of how you want to solve the equations of the AC analysis bias circuit. Okay, and we focus on common source and also voltage divider bias. Okay, and you need to know unbypass and also bypass condition. Okay, you need to know both condition for bypass and also unbypass. So later on, I will give to you. The example from previous question, like before, the example of previous questions for DC analysis and also AC analysis that related to MOSFET. Okay, so later on, please check on your e-learning. That examples of previous questions and also solutions, so that you can refer and you can maybe you will understand more if you look at many circuit examples, right? So today we end of chapter 5. Okay, so if you have any questions related for today lesson, you can always message me or email me anywhere, and if I need extra explanation, I will explain for the next class that we will meet later on. Yeah, so thank you and Assalamualaikum.